In our study of the elastic behavior of materials, we've given particular attention to ratios of stress over strain. So I want to circle back to the behavior of springs, and instead of talking about Young's modulus or bulk modulus or even shear modulus, let's go back to the ratio of stress over strain, just known as the K value, or the spring stiffness of a spring. The K value, according to Hooke's law, is just the force divided by the elongation of a spring. So stress here is measured in newtons, and the strain, instead of being the fractional or percentage increase, is just the actual increase. So it's not a dimensionless quantity in the denominator here. Our units for spring stiffness are going to be newtons per meter. So we know how springs behave on their own. What happens when you start to combine springs together in order to support an object? So here we have an object of mass m suspended by two springs. So it's going to have a force vector here. Let me draw a separate dot, make it a free body diagram. So there's a downward force of mg, and then there are two springs pulling upward. So there's no guarantee that each of those springs have the same stiffness, and so there's no guarantee that they each share 50% of the load. Maybe one of the springs has an upward force F1, and then the other spring has a larger force F number 2. So how do we figure out what single spring could do the same job as these two do in tandem? If we can figure that out, then we'd have something known as the effective K value for the replacement spring. So in other words, instead of taking the same mass and hanging it from the two springs, what if we just hung it from a single spring whose K value is this quantity K effective? Well, the one thing about springs connected in this manner side by side, what we call springs in parallel, is that they both have to have the same displacement, right? Well, they don't have to, but generally that's the way you want to set it up. So if this spring is stiffer, then actually maybe this support member should be a little farther over to the right so that the weight is hanging from not so much the center of mass, but something like the center of force for this system. So in any case, as the mass pulls down, this rod that the two springs are attached to remains horizontal. It doesn't end up tilting and favoring one spring or the other. Then if that's the case, they really both will have the exact same displacement. So in other words, if the two springs sitting side by side, which have a rod at the bottom, sit in this position when there's no load, then where they're loaded up with the weight, they've both stretched the same displacement, some value of delta x, when the weight mg is suspended. So let's look at this free body diagram one more time. If you just have a single spring, just take this apart and only have spring number 1, for example, and hang the weight mg from it, then without any weight hanging, the bottom of the spring sits here. With the weight hanging, then it's displaced some value, delta x number 1, and so the K value for this spring number 1 is mg divided by delta x number 1. And we could do the same thing if we were to picture just spring number 2 supporting the weight. We would say that K2 is mg divided by delta x number 2. But when the two springs are connected side by side, as in this diagram or this diagram, then the free body diagram suggests that mg is offset by F1 and F2. So to maintain equilibrium, F1 plus F2 would have to equal mg. Now what we'd like to do is find one single spring that'll stretch the same amount as the two of them when connected in parallel. So like we said, if the rod is initially at this elevation when no weight is hanging, and then when the weight hangs it drops to this elevation due to the behavior of both springs together, is there a single spring that we can find somewhere that would start out at that same original length, and then when loaded with the same amount of mass would stretch the same displacement as the two of them together. If so, we have found an equivalent effective spring constant. So in that case, we would have the effective force would also have to equal mg. Well, the effective force, according to Hooke's law, would be the effective k value multiplied by that common displacement delta x. Or we could say, according to Hooke's law, that k1 times delta x is the force in spring number 1. Added to that, k2 times the common value of delta x for the second spring has to equal mg. But since it's the same mg in both cases, we can equate these expressions. So you get k1 delta x plus k2 delta x equals k effective delta x. And since we're picturing these as all the same delta x value, then we can cancel that out of both sides of the equation. And what we find is when springs are connected in this manner, in parallel with each other, the effective spring constant is nothing more than the sum of their individual spring constants. So for example, if you had a fairly soft spring with a k value of only 50 newtons per meter, and that spring was suspended side by side with another spring whose k value is larger, maybe 200 newtons per meter. And then you attach a rod to the bottom of the two, and you suspend a weight. So now when the weight is hanging, the rod drops to a lower position. And there's this value of delta x. Well, is there another spring that when put under a load of the same value, same mg in both cases, would have the exact same value of delta x? Yeah. And the effective k value of that singular spring would just be, according to this formula, 250 newtons per meter. So it couldn't be simpler. To find the effective k value for springs in parallel, we'll just call this k parallel, all we have to do is add the k values of the two springs. And in fact, if you connected 3 or 4 or 5 or any number of springs together in parallel, the effective k value is just the sum of all the individual k values. So one way to say that is that the effective k value for springs in parallel is always greater than the greatest individual spring's k value. So in the next video lesson, we'll investigate what happens when you connect springs end to end instead of side by side and come up with an equation for the effective k value for springs in series with one another.